Hi, everybody. Welcome to our next round of IRIS-HEP fellow presentations. We're going to have a slight change in schedule. So the first up will be Santam, who was mentored by Yana. Yana, can you say a few words about his work?
Yes, hi, ladies and gentlemen. Without further ado, it is my pleasure to introduce you to our IRIS-HEP fellow, Santam Roy Choudhury. Santam is a third-year engineering student from National Institute of Technology of Dugapur, and during the summer, he had been working on automating awkward array testing. So Santam, the floor is yours.
Oh, yeah, thanks, Yana. So, hi everyone. My name is Santam. So, this past 3 months, I was working on the project to automate the awkward array testing. So, this is my project. So, first of all, before we get into the project, let's understand the current testing infrastructure that is implemented in awkward array. So we have a kernel specification file that is an YAML file present in the root directory of the code base. So this file contains various details about each and every kernel functions, like the function definition, the arguments, the argument names, types, and details. So we have a script called generate test.py, which basically takes in these arguments and creates a Python kernel. Now, this Python kernel is used to auto-generate the Python C and the CUDA kernel tests. And from there on, we generate the tests and then run it. So this framework has some loopholes, like there are not too many specific test cases. The testing is not specific to the errors, and the roles of the arguments are not well defined. So based on these loopholes, we come to the objective of the project. So the objectives are that we need to generate more test data. We need to store these data in a much more computer readable format, namely YAML, and we need to automate the process to generate the test from these data. So the testing approach that we took was that the code base has a lot of integration tests. So when we run these integration tests, it calls each and every kernel function. So the approach that we implemented was we fetched the data that was passed to these kernel functions. So let's say a specific integration test is run, and then that integration test will call a certain kernel function. And when it calls that particular kernel function, it passes in certain arguments and data. So we fetched those arguments data and we collected them as a whole. So that was the approach we used to get these raw data. So after we got a pool of raw data, the next step comes to processing. So we had a lot of data from it, and we fetched each and every arguments for each and every kernel functions, and we wrote a certain script for fetching the correct arguments from there and then cleaning them of special characters or enormously large numbers, and even for unwanted numbers when the numbers does not satisfy the length of the lists. And after we got a set of clean data, the next step came, we need to map all those data onto an YAML file. In that way, we got a complete list of data. So this is a screenshot of how the YAML file looked like. So we have a argument, a function, a kernel function, awkward in identities get item carry. So below that, we have all the tests there. So we have the inputs and the outputs over there. Another change that we brought into the code base was that we separated the role-based data from the function-based data. So initially, the kernel specification file had a set of role-based data. So we separated all those data and put them into the YAML file that we generated earlier. And so now all the data comes under one file and the kernel specifications on the other file. So ultimately, when we ran these tests, we got around 123. We got data for around 123 kernel functions out of 143, and total we had 2,673 unique test cases. So that was the overall result of that. So the future development plans that we planned on implementing based on this project was that we would analyze the test cases and look for bugs that are existing in the code base. And after that, we would be using those test cases to pave the path for kernel, CUDA kernel development based on the approach of test-driven development. So some of the things that I learned from this project was that some best practices for writing unit tests. And I got introduced to some Python libraries like PyTest, hypothesis, unit tests, then property-based tests, and so on. So, and also I learned best practices for preparing presentations for conferences. And I also got the chance to speak at IRIS-HEP on this work. And I have linked the video in this slide. So thanks a lot for listening to me. That was my project. If you have any questions you would like to ask, you can ask.
Thank you, Santam. Any questions for Santam?
Yeah, I have one. In the slide of the results, you mentioned that data for 123 out of 143 kernel functions. Could you elaborate on that? Does that mean that about 20 kernel functions did not work, or what happened to those?
Yeah, so like first of all, 143 kernel functions are the functions that we have to auto-generate. Like if you look at the kernel specification file, there is a value named automatic test. So whenever it is true, we generate a test for that. So that makes 143. And the remaining, like we have 123 kernel functions here. So the remaining ones, like the data was not right. And the data that we got in the pool of raw data, it was not satisfying the requirements for the arguments. Like some of the data had really long numbers, large lists, which were not passing the tests. So ultimately, like the data was not right. So therefore, we thought of not using these data and then analyze those kernel functions which were giving certain wrong data, if there was something wrong with it or not. And then after that, we can use those data in the tests.
Okay, thank you.
Any other questions for Santam?
Yeah, I had a quick question. Just like roughly, what's like the level of coverage? It seems like a really nice set of tests. I guess like how complete is the coverage for the whole awkward array?
So it has quite like we can say that. So let's say that I got a pool of raw data, and then from all that data, we can take consider that 80% of them are good data. So we can use those 80% data for like analysis and all that. So let's say if I give you a rough estimate, it would be like 80%, 85% like that of all the kernel functions that's there in awkward array.
All right, thank you.
Okay, any other questions? Next up is Farook Mukhtar. Farouk was mentored by Javier. Javier, can you say a few words to introduce Farouk's work?
Yeah, definitely. So Farook Mukhtar is a second-year graduate student and HDSI fellow at UCSD. He's been working this summer and a little in the spring on explainability and interpretability methods for graph neural networks, especially focusing on this machine-learned particle flow algorithm. And so he'll tell you a lot more about that.
Okay. Yeah, let me proceed. So yeah, it's about machine learned particle flow, and we're exploring, like Javier said, explainable AI technique on this MLPF project. So let me first start by giving a quick overview of the problem. So we're dealing with particle flow, or in short, PF. It's a global event reconstruction in the sense that it combines information from different subdetectors like calorimeter clusters and from the tracker, which are tracks and so on, to reconstruct particle flow candidates. And we're exploring MLPF, which is an alternative machine learned algorithm that uses graph neural networks to do this specific task. So our input is particle flow elements, the clusters and tracks, and our outputs are particle flow candidates. Brief overview of the ML model. It's a graph neural network which takes as input an event, modeled as a graph around 5,000 nodes, where each node is a detector element. It's either a cluster or a track, and we encode this information using one of the features of the node. So if it's a type 1, it's a cluster. If it's type 2, it's a track. And the output of the model is two things: the PID, which is a classification, like a class label of the node, and the P4, which is the regressed, like P4 momenta, like PT eta, some more information about the particle flow candidate. And in this problem, we have 6 classes we're trying to classify, and here is a class distribution, just so that you get a sense of what classes are mostly present compared to others. So these 3 classes are the most represented. And this is a visualization of the architecture. So we take the event as input, which is a set. We build the graph using KNN. And once we've built the graph, we do a step of message passing, and then we feed it into several layers of deep neural networks to make the prediction. And you can find the link to the MLPF paper and the dataset and the code on the bottom left of the slide. Now on slide 5. So the project goals for this project was 2 things. First, to develop a different training setup for MLPF using PyTorch compared to the paper which used TensorFlow, and to implement an explainable AI technique called layer-wise relevance propagation on MLPF. And here's a quick overview of other recent developments by the team, which we have a bigger team which participates in this effort. So some of the effort is to make CMS software integration of MLPF, transfer learning, quantization, and hyperparameter optimization. So for the performance, here's the result for the full training. And you can see basically in all of there are different plots which we can use to assess the performance of the model. And we're always comparing to the rule-based algorithm to see if MLPF is really working. And from these plots, we can conclude that there's comparable performance to the rule-based. So for example, on the left, we have the confusion matrix, which assess the classification part of the model. And you can see that MLPF is doing from this plot slightly better than rule-based. And there are other plots like particle multiplicities. You can also see that comparable performances throughout. Now for the second and probably the part that took most of my time was the interpretability. So we're exploring a technique called layer-wise relevance propagation. And basically it's a technique that computes or that allows you to compute a relevance score for each neuron in the network. And so you can then start answering a question like this, which detected elements were the most relevant when making the inference. And so we attempt to draw a relevance score matrix, or what we call a relevancy map, which is a heat map of relevance scores for each classified PID that shows the relevant parts of the graph for this prediction. And here is the, I guess the most famous picture of LRP, which and the formula which explains how the relevancy scores are computed as you go backward throughout the layers of the network. Of course, this is shown for a simple MLP. For graph neural networks, it needs to be adjusted a bit so that it works in the same way. Now let me show some samples of the relevancy map I was just talking about. So this is one example. This is one heat map for a charge hadron, which was correctly classified. And the different rows here correspond to the neighbors of the charge hadron, ordered by the separation from the charge hadron in eta phi space. And the columns are the 12-dimensional input features of these different neighbors. And the Z scale is the relevancy of that particular feature of that particular neighbor. So as if you look at this heat relevancy map, the takeaway would be perhaps that the PT, which is the brightest, the PT of the charge hadron itself was the most relevant feature when classifying the charge hadron. And another note would be that the neighbors were not really that relevant for the prediction, and hence why it's just black. There are no colors there. This is another example of a sample, another sample of the same like a different correctly classified charge hadron. So same problem, but a different result. And from this, you see, for example, that neighbor number 2 was also relevant for the prediction, hence why it has some colors over some of its features. Now, processing the relevancy maps is somewhat difficult because we have one relevancy map per output neuron, and we have in this problem 12 output neurons per node, because we have 6 classifying PIDs, the one autoencoding 6 classes and the 6 regressed variables, the P4. So we have 12 output neurons per node, and we have 5K nodes per event, and we have 5K QCD events. So we have around 300,000 relevancy maps. And so we needed to find a way to systematically process these. So we've tried 2 things. One is averaging over relevancy maps after ordering neighbors by relevance. And the other is making histogram plots, and I will show both of these in the next slides. So as for the averaging, so we take the heat map, and like I said, we order the neighbors. Instead of ordering by separation, we order them by relevance. So we assign a relevance score for each neighbor, and then we average across the different relevancy maps. And for example, this is one of such averaging for the electrons. And if you compare both of these, the one on the left is average across correctly classified electrons, the one on the right over incorrectly classified electrons. And you can see that for the correctly classified, this particular feature was bright, and the incorrectly it was not bright. And when you look at this particular feature, basically it tells the model if there is an electron. It's kind of a hack, but it's how Delphis work. It has a feature called isGen electron, and it sort of makes sense that LRP finds that it's relevant when it correctly classifies electrons. Now the final plots I'm about to show are the histogram plots, and for these, when we process the heat maps, we just start counting the fraction of nodes that have a certain R scores, and then we compare the different features for the different classes. So for example, the one on the left, it's for all charged hadron nodes, and you can see that all of these features have different levels of importance, let's say. So for example, eta, since it's more towards the left, then it has less R scores on average than the other features. Eta is the green one. And if we compare it to the neutral hadrons, for example, we have the eta outer, almost non-existent, as you can see. So basically, we do these histograms for the different classes to start picking out the most relevant features for the different classes. So summary and outlook, we developed an alternative baseline MLPF model using PyTorch, and we explored the application of LRP, an explainable AI technique, on MLPF. Now, further steps are model optimization, for example, the time complexity, because in the current or the planned upgrade of the LHC, we'll have a bigger pileup. So it's good to revise the algorithm and make sure it scales well with the number of inputs. Also, we're exploring quantization, and we can also try to use LRP to understand better the model's decision making, and maybe furthermore deployment on new hardware platforms and application to CMS, to real CMS data. And thank you. That's all from me. I'm happy to take any questions.
Thank you, Farouk. Any questions for Farouk?
Hi. You mentioned at some point that for the relevancy maps, you had to make some adjustments for GNN, graphical neural networks, I believe. That's that right there. Can you mention what sort of adjustments you made, I guess?
They're not so much, like, they're not fundamental adjustments. It's just that these, when they work, like the way they're presented now is that you redistribute the R score of a node across its the same node's latent feature space. So different nodes don't talk to each other during this procedure. But once you have a graph neural network and you have a message passing step, you have to redistribute the R score across the different nodes instead of the same node's latent feature. So it's just the way you redistribute is instead of redistributing across one dimension, you have to distribute across a different dimension. I'm not sure if maybe that's the best explanation.
By different dimensions, let's say like it going with the image. So it goes outputs and you have 3 nodes there. By dimensions, you mean like the next one on the left or downwards by each node?
Yeah, so if we think of the graph as, if we try to model it as a let's say 2-dimensional matrix or an image, and you've got the nodes as the rows and the features as the columns. So instead of redistributing the R scores across the columns, you start redistributing them across the rows, or the other way. That's what happens with the message passing, because you're trying to redistribute the R score of one node across its neighbors so that they have their own take on the prediction of the node.
Awesome. Thank you.
Any other questions for Farouk? No. Thank you, Farouk. Up next, we have SUKHANA, who was also mentored by Javier. Javier, you want to say a few words?
Yeah, happy to. So so Suki Krishna here. She's a 3rd-year undergraduate student at UCSD. This summer, she's been working also together closely with a team of colleagues at CERN on graph neural network autoencoders for anomaly detection in the level 1 trigger. So looking how to shrink these complicated algorithms to potentially fit on FPGAs. So take it away.
So hi everyone, my name is Sukanya Krishna, and I am mentored by Dr. Javier Duarte at the University of California, San Diego. As the title suggests, my IRIS-HEP project is to work on particle graph autoencoders as a real-time jet anomaly detection technique to search for new physics. So in the LHC, there are these real-time triggers, such as the L1 level 1 trigger, which is a real-time data filter system that rapidly decides which collision events to record. And this requires smaller models because of the low latency budget of around 4 microseconds and other computing resource constraints. So this means that only certain models can be translated and only certain small models will fit into the trigger. For this reason, we want to put anomaly detection autoencoders onto the trigger and run tests of those algorithms on FPGAs, which are circuits that can be programmed to perform various computational tasks. So what are autoencoders? Autoencoders are structures that are composed of an encoder and decoder that are each a neural network trained to accurately map a set of input data, in this case, representing known physics, down to a compressed latent representation in order to encode the most significant details found within the data set, and then reverse those encodings to their original form. So for anomaly detection, by quantifying how inaccurate this reconstruction step is, by measuring the difference between the original data point and the reconstruction as an anomaly score, we can determine whether potential anomalous candidates for new physics exist within the data, where data points with high reconstruction error are considered to be anomalies. Variational autoencoders, on the other hand, make both the encoder and decoder probabilistic. So they describe the latent features, the latent attributes using a probability distribution. That sample distribution is then used for the reconstruction. The potential advantage VAEs have over AEs is that a VAE provides probability measure, which is done with the addition of KL divergence to the loss function, which compared to reconstruction error may be more objective in judging whether a particle is anomalous. So with this information in mind, my project objective is to investigate different types of autoencoders as well as variational autoencoders to determine which structures can be best optimized to fit in an FPGA to meet L1 trigger requirements that is also good at anomaly detection. To do so, we are evaluating variations of autoencoder and variational autoencoder structures on which structure can be best optimized to minimize the reconstruction loss, as which structure is best at anomaly detection based on the threat curves. And then another objective is specifically looking at graph neural networks, which are models that apply machine learning on graph structured data of nodes and edges as an alternative to convolutional or fully connected networks for anomaly detection. So the data set that the models are training on is the CMS L1 trigger simulation. We have simulated background or QCD and multiple and signal, specifically 15 signals of various kinds of physics signatures. This data set represents 19 objects, specifically 1 MET, 4 electrons, 4 muons, and 10 jets. And for each of those objects, we have information about the PT, beta, and phi. So now let's talk about the different kinds of models that were evaluated themselves. So the main difference between the model types is the kinds of layers used to build the encoder and decoder of the autoencoder. So we have, we evaluated some baseline models, models that have already existed from this cited paper, which are being evaluated to cross-check and compare results. So we have a dense autoencoder model, which learns based on every computational unit in the received input and will output a fully connected layer of the same dimensions as the previously received one. We also have a CNN-based autoencoder and variational autoencoder model. Convolutional neural networks are usually used for images and matrix structures. They preserve the location or local structure of the input data and apply convolutional filters to regions of the layer to capture key features that will be referenced during reconstruction. On the data set, this model is being applied to the matrix of inputs as if it were an image where the matrix of inputs is the number of objects by the number of features. And then we have our graph-based models, which are the interaction network, autoencoder, and variational autoencoder model. Interaction networks are designed to, interaction networks reason how objects in complex systems interact. So ions are designed to analyze the interactions or properties of distinct objects and relations in complex systems. In particular, we apply an ion architecture to learn a representation of the input graph and then use it to accomplish a classification task, which in this case is whether an event is anomalous. To learn this new representation of the input, a set of input features describing each edge or pair of nodes on the graph is replaced with a set of engineered features specific to each edge and whose values depend on the connection between the nodes on the graph. So for this task, some key features of the model architecture are 2 neural network inferences to run the neural network on each edge and output a vector for each edge, and then for a certain number of learned features. For each node, send out a specified number of output features. Then there are message passing steps to get the summation of latent features for each edge that will be sent to the receiver node. So here I have some ROC curves for the models that seem to produce some of the better results for anomaly detection at the moment. Each curve on the ROC represents a classification problem, classifying background versus signal for each of the signals. The AUC values indicate the percent of accurate discrimination between the background and signal. So if we analyze these plots here, we can see that the convolutional variational autoencoder and the IN variational autoencoder seem to produce some of the better results for some signals, with the conv being the best, where AUC values for some signals are reaching over 70%. We're still working on these models, studying why that is the case and also other variations that may be possible. I also have some reconstruction plots for each of those models on one object, the MET. If we analyze the plots here, we can see that the reconstruction for all the models are pretty good, but the IN model has the best reconstruction performance. So overall, as a general summary of the project, I have experimented with dense convolutional and interaction network autoencoder and variational autoencoder architectures. The results indicate that there is better reconstruction performance by the IN VEE, and but the convolutional VEE has better anomaly detection results. So for next steps, it is to validate the performance of these models with existing results and then investigate converting these models using HLS4ML to FPGA firmware. Here I also have linked the Git repo for this project for those that may be interested. Finally, I would like to give a big thanks to Principal Investigator Dr. Javier Duarte, postdoc Dr. Daniel Diaz, and grad student Raghav Consul. These are incredible people that I was able to learn a lot from and really guided me throughout the course of this project. And finally, I would also like to give special thanks to IRIS-HEP for this entire opportunity. I will conclude my presentation. Thank you very much.
Thank you, Sukanya. Any questions?
Hi. I have questions on the rock curve slides. Yes. So we see the convolutional autoencoder was the better one. So this is based on the accuracy you mentioned, right?
Yeah, the metric that's being used is mainly the AUC values, and you can see like them for each signal on the right.
Okay. It's just that I guess I just see this and kind of see it as messy. So I don't know, based on the shape of the rock curves, were you expecting a certain shape to know that this is looking good or bad?
The shape is so I guess like the shape can sort of vary. Rather than shape, I think we're mainly looking at the AUC values. So I think ideally we would want the rock curve to sort of like approach 100% in the true positive, right? I believe. So it should like sort of level off in that direction.
Yes. Thank you.
Let's see, I see someone has their hand raised.
Hi, I guess that's me. This is Josep. I was wondering on slide 10, these MET plots, do you have any hypothesis why the prediction is somehow a mirrored version, whereas the true is kind of a delta function, for example, this conv VAE, or maybe in general, what's going on there?
Could you reiterate that? Like, why does the...
Yeah, sorry. So if I look at the conv VAE, for example, I see that the MET true distribution, there is like this kind of big peak at 2000. And then the prediction is kind of different from that. And I was wondering, do you know what's going on there?
So I have an idea. So 2048 is the maximum MET that can be gotten from a digitized value, because the L1 trigger only allocates a certain number of like bits to it. And so if it's above that value, it's just set to 2048, which is why there's a big spike at this point. The prediction is just based on how the reconstruction algorithm works. So I believe that's why it sort of looks like this.
Okay, thanks.
Okay, any other questions? No? Well, thank you to our fellows. The talks were great today. And also thank you to the mentors for your work as well. That's all we have for today. More to come.